All right, so last time we went and we found the solution for the concentration as a function of position across our membrane, and we showed that it indeed is linear, and this was the equation that we derived. What we're going to do is just take a look at some conclusions from this and also make some observations. So one of the things we found was the concentration gradient is linear. I've mentioned this several times. And we found that if we were to take a look at the flux, right, fixed first law, because that's what we want in this type of problem. You recall that we were asked what the flux was through the film thickness. Well, the flux is given by minus d dc dx. And dc dx now, since we have c, we just take the derivative of this and we get minus 2100. So we now have dc dx to put in here, and then we can calculate the flux. Now notice that if we put the cdx in here, this is a constant, right? It's not dependent on x, and d was a constant in our problem, and so this tells us that the flux is constant. So everywhere in our solid in steady state, we have a constant flux. Okay, and that's what we have. Now, I guess the question is the flux being constant a condition of steady state or a condition of our assumptions? And so we'll take a look at that one later as we look at some other problems. But right now, the only condition for steady state is that our variables don't change with time. Okay? But nothing says that the flux can't change with position. In this problem, it doesn't, but it doesn't mean that it can't in some other problem, for example, maybe the cylindrical case. So we'll look at that one very soon. All right, so this is what we found. And remember, these conclusions are only valid for our experimental conditions and assumptions. It's very, very important. This is a one-dimensional solution. We assumed steady state. We had fixed surface concentrations. We had a constant diffusivity and a constant cross-sectional area. Okay, so these two are very important. If we violate these, then these conclusions may or may not be true. All right, so some things for you to think about. I'm not going to give you the answers for this one yet, but we'll talk about this in class a little bit. But what can we do to increase the throughput for this diffusion cell process? How can we pick up this flux value? Let's say if we were using this to purify a gas, and so we wanted to allow the gas that we want to diffuse through this membrane and leave behind impurities. But we need to be doing this fast enough in order for it to be economical. So, we could think about things like increasing the diffusivity, increasing the concentration, maybe decreasing the film thickness, and perhaps there's something else we can do. But I want you to think about this, how do we do these things? Are there limits on how much we can increase these or decrease this? What problem does this create? If we, say, for example, decrease the film thickness, and what else could we do to increase this throughput? And so, again, I'll bring this up in class, and I'll give you guys some time to discuss it with each other.